Good evening and welcome to the final edition of this year's Stargazing Live. And what a week we've had here at Jodrell. At the end of a day which saw the sun smile on the UK, tonight we'll be bringing you all the highlights of Britain's most spectacular astronomy event so far this century.
And on top of all that, all week long you've been searching for supernova, and tonight we've got a bit of news.
Yeah, you've helped revise the known age of the universe.
I'm Brian Cox, he's Darragh O'Brien, and this is Stargazing Live.
Well, what a day it was. It's only 12 hours ago that people up and down the UK enjoyed one of the great celestial events. People, that is, who weren't, say, at work or maybe underneath clouds, right? So for some of you, this is your first chance to enjoy the incredible eclipse. This is the display we saw this morning. It was an incredible morning, and this was the moment that it all started. In the southwest at 8:20 this morning, we had first contact in Plymouth, down in Cornwall, and then that moment of first contact moved up through the country. 8:27 it was in Jodrell.
I was say that. You see the clouds passing over there.
That was the first time the clouds went. The first time the clouds went when they appeared. Leicester had a clear day as well. And then about an hour later, the moon moved across. We reached maximum coverage round about 9:30, 9:23 in Newland. There's the sun smiling there, first sight of that. Here in Jodrell Bank, I believe, it was a little bit later, about 9. Stonehenge got in on the act about 9:29, and we were there a little later as well. And we knew there were many of you around because you sent in many, many photographs for us.
Yeah, these are pictures of people, you looking at the eclipse. I thought there was the real sense of excitement. There was at Jodrell and everywhere around the country, I think. This is a picture from Alan Fitzsimmons. They are, I'm not sure what they are, actually.
This is in Devon, apparently.
Oh, it's in Devon, is it? I don't know what this one is. It's Barney Nichols. It says here, bunny shadow.
OK. Oh, hopefully you can all see that, because I can see that.
This one I love, from Chris C in Penzance, because we said that you could use a colander if nowhere else as a last resort, project using a colander.
I don't think we even believed that was actually going to work.
So you'll see this first contact scattered all over there from the colander. I'll give you one more. This is lovely. This is a father and son, Jay Mason, in Newcastle upon Tyne, looking for the eclipse.
So that was as it passed across the UK for the partial eclipse. By 9:41 a.m, totality was approaching in the Faroe Islands, and we crossed over to see what it was like on the ground with Chris Hollands.
The shadow is 5 seconds away. The totality is 5 seconds away now.
Here we go.
And you're really cooling down. The temperature has dropped another degree. And the wind has dropped now as well. And now it really is darkness. We're 7 seconds into the totality now. We're standing in the shadow of the moon.
So this is totality.
We are in the shadow of the moon, Chris.
So while Chris was on the ground, we had sent Liz Bonin into the skies, and this is the moment she saw the totality.
It's still surprisingly so bright, despite the fact that there's only a tiny sliver of the sun left. This is Bailey's Beads I didn't realise they were going to be so bright. Look at that. And it's almost like one ginormous diamond ring left, set in a circle of brightness, encircling the moon shadow. Oh, are we seeing features that look suspiciously like prominences? This is where the chromosphere becomes visible. There it is, the diamond ring. And we have reached totality.
Well, Liz has made it back, and she's here with us now. Welcome
Just
back.
about.
I just said that footage. It's you sound emotional in that footage.
I really was, and when you were describing the eclipse that you saw in India on Wednesday night,
Yeah.
and I've heard it from others who've seen total eclipses, it's like, okay, I get that it's amazing, but it's only when you actually experience it that you realise just how emotional it does become, aside from all the science and all the celestial mechanisms that you're seeing, you know?
And also, I was talking to Chris Lintott earlier, because we're here at Jodrell, we saw what most people saw across the country, like 85, 90% eclipse. And we thought, well, it's not going to be that moving, that spectacular. But I think it genuinely was. Yeah. It took me by surprise how wonderful it is to see the moon sweep over the surface of the sun. And as I said, he got back. Usually the behind-the-scenes stuff isn't that interesting, but in this case, you had an interesting journey.
Yeah, a really interesting journey. A lot of challenges. I said last night that we had to be in the right place at the right time, but we had problems with our communications links, and also we had 100 miles per hour crosswinds. And so we had to change. We threw the flight path out the window, not literally, and just did smaller loops over Aya just to keep in touch with the receivers, and also had to change the lenses because the turbulence was so great. And so it meant that we didn't have as long runs perpendicular to the sun to get you the images. So we fell off air, didn't we, at one point?
Yeah,
when I was
we did. I
talking?
mean, we were incredibly good. About 5 to 9, we had no word from the plane.
We had no
got
comment.
totality. Yeah, and then the first link we went back to, it froze completely.
Yeah,
so we
yeah.
could have lost
And when you
entire-
came to us first as well, we just weren't in the right position because we couldn't do these long perpendicular flybys as we had planned because of the communications problem.
But you captured some incredible images from the only place they could be captured as well, because there's nothing to be seen from the islands of the Faroes. And we have totality here.
Yeah, no, it was extraordinary. And, you know, the corona is a million times fainter than the disk of the sun. And when it appears, I mean, you know, this is a really great image. To the naked eye, it's even brighter. And then I couldn't believe how many prominences we could see, even extended loops there. A greater loop formed by the linking of a couple of different
Explain to the
prominences.
prominence, because you said that. Look, there's a prominence on the day. But what?
It's plasma, it's activity on the sun. Sometimes they break off and form coronal mass ejections. And we saw quite a few, and they originate in the photosphere and extend out into the corona.
That pink object there, that's a prominence. How huge is that?
Well, you know, how many Earths can you fit in the sun again?
About 100. So it's like a million Earths to fit inside. About 100 across.
Across. So that could be the size of the Earth.
Yeah.
Right? That's how big these prominences are. It is a solar maximum at the moment, isn't it?
So it's particularly busy, right?
It was just amazing.
What I thought was wonderful as well when you were talking about it, because you did the same as me. I think you forgot you're on television. I think, didn't you?
I did it with the Aurora last year. I did it again. I said, just don't talk that much. I forgot about being on the telly. I did.
I thought it was beautiful when you said, "What's that?" And that prominence appeared, which nobody expected.
Yeah,
I think.
we
It was
really
so
did.
Bright,
Not with a solar filter. We didn't expect to see such a
Let's have a look as well.
big
So we
one.
can have a look at the diamond ring that appeared, because that was particularly impressive when
So
totality
after
ended.
totality, yeah, that was quite an extraordinary image. And that's the chromosphere right there. That's sort of the inner atmosphere, you know, the layer before the corona. And yeah, as the moon moved to the left, it appeared and it grew and grew. It was just a beautiful sight, it really was. Excuse the turbulence. Mark Pengil was doing his absolute utmost to keep it in frame, but, you know, 100-mile-per-hour winds that way. It was a bit tricky.
We spoke about that coincidence as well, and you know, earlier on in the week we were talking about it. You go, yeah, coincidence, 400 times further, closer, 400 times down. But look at that. I mean, it is an incredible coincidence, isn't it? You see the perfection of that alignment.
The moon is actually in perigee at the moment, so actually it's a tiny bit bigger than the sun right now. So to actually get the chromosphere was quite something. We didn't expect to get so much detail, you know, beneath the corona.
Yeah. Okay, now we're going to have more exclusive views to come of that later. But it's not all about the eclipse tonight. We'll be bringing you news about your search for exploding stars, for supernovae. And we have been inundated with your photos of Orion, which we're going to pull together to make the best ever picture of the constellation. Loads of amateur astronomers have sent in their photographs, including this one from this young man. This is Professor S.W. Hawking from Cambridge, making a name for himself in the world of physics. There's Professor Hawking, who sent in a photo to add to the group of photographs, which will only make it a greater picture.
That's wonderful, isn't it? Now, also this morning, if you watched, you'll have seen that Lucy Green was at a star party in Leicester, and Lucy's back with us now. Welcome back, Lucy. And I wanted to ask you, because you're a solar scientist, so your professional life is spent studying the sun, and I know all eclipses are different. So, was there anything special you noticed about this one?
All eclipses are different, you're right, Brian, and this one was incredibly special. I was so pleased to be able to see it. And I think what stood out for me was, even though the sun was only 85% covered here in Leicester, we still felt a noticeable drop in temperature and a noticeable drop in the light. And the light changed into this very mysterious hue, sort of a purpley orange colour. I've never experienced anything like that before.
You know, we were chatting about that back here, actually, and we decided, we have a theory, which is that because it's dusk, so the light falls away, but in the daytime, then it's not like a sunset where the sun gets redder and redder and redder. So that's our theory about why the light changes in that strange way. What do you think?
I like that theory. I think it's got to be to do with the fact that it's a different kind of shadow. And of course, I was joined by over 600 school children as well, experiencing that very strange effect. But not only that, we had a lot of other activities going on because schools around the country were collecting weather data and they've been sending those in. We also launched a high altitude balloon to try and capture a shot of the eclipse. That balloon has since been retrieved and the team are frantically going through the images. So we will bring you some more of those, we'll bring you some of those later on. And then finally, of course, we have our telescope set up, and I will be using them to find out more about our most familiar star.
Lovely stuff. Thank you very much, Lucy. Now, in the Netherlands, the European Space Agency this week have given us incredible access inside their spacecraft testing centre. Dallas Campbell is there. Let's find out what he has in store for us tonight.
The room that I'm standing in at the moment is the LSS, the Large Space Simulator, which does exactly as it says on the tin. It recreates the harsh environments of space here on Earth. And they could recreate the extreme temperatures that you are likely to encounter in space as well. They can get it very, very cold, down to around minus 173 degrees Celsius using liquid nitrogen. And they can also recreate the sun's radiation. Behind me, just tucked off to the side, are huge 6-meter walls of xenon lamps, which get reflected off that vast mirror that you can see beside me. Every single vehicle that goes up and out into space. We'll spend weeks in here making sure that it's up for the job. Now, in a few minutes, I'm also going to look at another ESA project. I'm going to look at their IXV, which is their new experimental space plane that they've been using for re-entry. And I'm also going to be looking at how they test the bone-shaking vibrations of a rocket launch.
We have, as ever, a suite of learned and wise guests tonight to answer your questions as well. If there's anything you want to know about today's eclipse, the sun, supernovae, send your questions in to us. The addresses you need are on screen now. The undoubted star of today, however, even though it's hidden behind the moon for a very important moment, was, of course, the sun.
Now, we get excited about eclipses, not just because they're spectacular to watch, but because they give us a rare opportunity to study the parts of the sun that we don't fully understand. Because even though the sun is our closest star, it still has plenty of secrets. The first odd thing you should know about the sun is that we can't actually see most of it. Our eyes evolved to see visible light, but that's just one part of the electromagnetic spectrum. The sun also emits wavelengths we can't see, like infrared and ultraviolet. This is the sun in visible light, but switch to ultraviolet, and it's a completely different world. The raging, turbulent surface lies beneath a towering, fiery atmosphere. And just like our atmosphere here on Earth, the sun's atmosphere enjoys some wild weather. It rains on the sun, but instead of water droplets, it rains searing hot plasma. In this solar downpour in July 2012, droplets of plasma the size of small countries fell towards the surface at 200,000 kilometers per hour. And if that's not strange enough, the length of a day on the sun varies from around 25 Earth days at the equator to about 30 at the poles. That's because the sun's equator rotates faster than the rest. And as it does so, it drags the sun's magnetic field with it, twisting it like a rubber band until eventually it snaps, releasing jets of energy that travel across space to Earth, where they can damage our power grids and disrupt communications. Today, we're able to view the sun with unprecedented clarity. That's because we have ultra-high definition cameras on board ever more sophisticated telescopes in space. Some of the most impressive images to date have come from the Atmospheric Imaging Assembly, or AIA, launched in 2010. AIA captured this massive solar eruption, nicknamed the Ink Drop, in June 2011.
When I came in the morning after this occurred, suddenly there was this big black blotch, and I thought something terrible had happened to the camera. And it was only after sort of 20 or 30 minutes where you saw the whole event, we realized it was something that happened on the sun.
This was the biggest ejection of material ever observed from the sun. And just 3 months later, the telescope captured something equally remarkable. Our first close-up look at a solar tornado. A twisting column of searing hot gas and plasma, thousands of kilometers high. It's hoped the images of these fiery towers could help solve a long-standing mystery about our sun. The further you move away from a heat source, the cooler the temperature should become. But on the sun, the opposite happens. High up in the sun's atmosphere, the temperature is actually around 100 times higher than it is on its surface. One theory is that solar tornadoes transport energy upwards, but we're still a long way from a complete understanding of our sun. Until then, our star, which appears so familiar, will remain a strange and mysterious world. Well, now joining us is Professor Richard Harrison from Oxford Rutherford Appleton Laboratory. Richard, thanks for joining us.
Richard, we want you to do sort of a post-match analysis on some of the pictures that we got today. Particularly, we have this image we have of the corona here, and we've already mentioned a few times, particularly this here, this prominence here. What is going on there?
The corona is actually, it's the sun's atmosphere, but it's not like the Earth's atmosphere at all. It's actually dominated by, and it sounds a bit abstract, magnetic fields. The Earth has a magnetic field, of course, but the sun has a rather dramatic, complex magnetic system that varies with time, and it traps the hot plasmas, the charged gases, in different sort of magnetic structures that you see, and you've seen in the film just now. And that structure that you see there varies with time, and you can pick out the features that relate to those magnetic fields as you see the eclipse, as it were, and from spacecraft and all the time. And you point to this in particular, the prominence that you see there. That's actually material that's actually trapped in these magnetic structures like a cool cloud. By cool, I mean tens of thousands of degrees. The rest of it is at 1 million degrees.
So this isn't exploding out?
At the moment, it's not exploding out. The the material you see in this prominence here is part of something that can erupt in an event called a coronal mass ejection, which is one of the most dreadfully named things in astronomy for something so dramatic, where 1 billion tons can come flying out into space in one go.
And you referred there to the idea that the corona is significantly hotter than the surface.
Yes,
No,
yes.
A bit of physics. Then if this is hot and this is cold, then you'd expect there to be a temperature gradient across there.
Yes.
But it gets hotter and hotter and hotter and then colder. So do we know why?
It does seem strange. The surface of the sun is a little bit lower than 6,000 degrees. The atmosphere, corona, 1 million degrees or so. It's an anomaly, if you like, but it's sort of explainable in the sense that we can think of lots of ways of getting energy up there because of all these magnetic fields. If you look at the sun in extreme ultraviolet light, for example, you see something that looks like a writhing plate of spaghetti with all these magnetic fields interacting. And you can generate waves and little flares and things that can dump energy into the corona and heat it up.
We've got a photograph, actually. I think we can take it of the sun. Not that one, but the next photograph of the seething surface.
Absolutely.
Can we first see, so if we can get it?
It's a dramatic sight.
Okay. We're not going to get that, so let's talk about this instead.
Absolutely.
In fact, yeah, if we go back to that double image, because we got an image very early in the process, and we weren't sure if this is an error on the camera, but then it stayed there, and that is a sunspot.
That's a sunspot, and that's, of course, what most people think of in terms of solar activity. That's the one thing a lot of people know about. And this is the sort of traditional view of the sun, isn't it? Other than the big bite taken out of it. This unusual view of the corona and its complex atmosphere the sun has is a little bit more unknown, if you like. And that sunspot, of course, might be perhaps a little bit smaller than the Earth, but that sort of size. And it's where magnetic fields actually break through the surface of the sun, if it's got a surface, into the atmosphere. It's a display, if you like, of the activity in the sun.
Well, now we've got that image. It's from the Stereo spacecraft. We were talking about that seething surface.
Right.
And this is actually a special image because it's going to be an image, as you see,
You'll see in a minute why, yes.
of an eclipse from space.
Right.
There it is. That's an eclipse in 2007, actually.
Yes, the Stereo spacecraft went out sideways. We have instruments aboard both, and they basically look back at the sun and the Earth and the space between the two, so that you can see if something is coming our way, basically, and understand the relationship between the sun and the environment around the Earth. This was a view shortly after launch, as it were, as the spacecraft was, or one of the two Stereo spacecraft was heading away, and the moon went across the sun and looked tiny by comparison to the eclipse we saw today.
What are the big areas of research now? There's obviously many about our star, but what are the big questions we'd like to answer?
Well, in this image here, you're looking at the sun in extreme ultraviolet light, which shows you this atmosphere. It's actually quite low in the atmosphere here. You can see lots of patterns and things on here, lots of complexities, mainly due to the magnetic structure in the sun's atmosphere. It's driven by the plasmas inside the sun. These active regions are the sites where you have the sunspots, but the magnetic structures you see in here, the big loops trapping the plasmas, that's where you get the flares, the big explosions in the sun's atmosphere, or these clouds, these coronal mass ejections come flying out into space. Trying to understand those and predict when those are going to occur. The physics behind those is a big driver.
And of course, they're not only of academic interest in a sense, because they can threaten the Earth, genuinely cause problems, can't
and
they?
you have some illustrations of this kind of thing, especially this one as a sequence. If you keep your eyes down here as it runs, if it will run, yes. That is a wonderful explosion, eruption in the sun's atmosphere where you get a solar flare and a coronal mass ejection together. 1 billion tons leaving the sun, a lot of it rains back down, but it's that sort of amount flying out into space, and what you're saying basically is, well, what happens if it comes our way?
Well, actually, you should say that very briefly, because I did use the word threaten the Earth, so I just want to make sure that people don't think I'm being too apocalyptic. What happens?
We shouldn't paint it as too much of a doom and gloom thing, but of course the arrival of a magnetic cloud, because that's what it is. At the Earth, we live on a magnet. The interaction of those two magnets, if you like, can drive a whole bunch of things, energetic particles flying in with this thing and so on. So you could be talking about pulses in systems, power generation systems and so on, where you can get blackouts, burnt out transformers or whatever, satellite control systems having problems, communications problems.
He loves one apocalyptic scenario.
Exactly.
Every series
this
is one
extreme
apocalyptic scenario.
It's a minor apocalypse.
I love an apocalyptic
The lights
scenario.
go out your mobile phone.
love it.
It's not an apocalypse
We
per se.
actually get 2.5 days on an apocalyptic scenario. Thank you very much. Richard mentioned some of the probes that are going and examining the sun. It is incredible what these probes can do once they're in space. But the toughest of the challenge they face is often getting off the launch pad.
Now, Dallas Campbell is at ESA's Technical Centre in Holland, and he's got news of the latest European spaceship to make it through that barrage of tests.
Yeah, thanks, Brian. No apocalyptic scenarios here, thank goodness. But I would like you to meet ESA's exciting new spaceplane. It's called the IXV, the Intermediate Experimental Vehicle, and this is it here. And it kind of starts, really, hopefully, a new chapter in cheaper, reusable, more manoeuvrable re-entry vehicles. And recently, they've put it through its paces. Launching the craft into space is the relatively easy part. Returning it back to Earth is much harder. Parachutes should automatically deploy to break its fall as it plunges back towards Earth's surface. To test this crucial safety system, ESA carried an IXV prototyped by helicopter to an altitude of 3,000 metres and then dropped it. The chutes unfurled and it made a perfect landing. But the next test would be far more punishing. Just last month, the craft was blasted into space on a Vega rocket from the European spaceport in French Guiana. This time, ESA wanted to test re-entry into Earth's atmosphere. Hurtling through our planet's thick layer of air at 28,000 kilometers per hour generates a huge amount of friction. IXV must withstand temperatures of 2,000 degrees. The base of grey ceramic tiles is a heat shield protecting the craft and eventually the crew inside from this inferno. The tiniest flaw could spell disaster. And after a nervous wait, it returned from space intact and splashed down in the Pacific Ocean. It had travelled over 25,000 kilometres, experienced temperatures that would melt rock, and survived, passing its toughest test yet with flying colours. And here it is, here's the IXV back on the ground, safe and sound, much to the delight, I suspect, of Giorgio Tumino, who's in charge of the IXV project. Now, let me just clear this up, because there's actually two IXVs, isn't there? Am I right in that? There's the one that actually did the suborbital flight, and another one that did the drop test. So which one is this one you've got
Exactly.
here?
This one is a model that we used to perform some in-flight testing before the actual mission into space. So with this model, we have tested several subsystems before bringing them to space, so to reduce the risk during the mission. And it was quite successful.
They were both successful.
Yes.
I tell you what I'd really like to do is actually have a little wander around, because I think this is the most extraordinary craft. It's I suppose, just looking at it, it's somewhere between the space shuttle and the traditional, I suppose, capsule, the Apollo Command Module capsule. NASA also developing a capsule, the Orion capsule. So where does this fit in?
In fact, this is, let's say, an ideal design which optimized the benefits of a capsule, which are the simplicity without the limitation, which are the lack of controllability and maneuverability, and the performances of a space shuttle type of spacecraft, which has high controllability and maneuverability. And with this one, we have the optimal compromise, high maneuverability and controllability, simplicity, and it has performed a fantastic mission with a very high precision landing.
Well, that's my question. Even without wings, I mean, are you going to get the same precision that you would do with wings? It's simply because you've got a lifting body?
Definitely yes, because it uses its own shape to generate the lift, so to steer and maneuver throughout the re-entry corridor to aim at the precise landing spot. And this is what was demonstrated last month.
So this is very much a prototype, and I know you had over 300 sensors on board, sort of collecting data and information. And have you had time to process that? And have you learned, and where are you going to go with it?
We have started to evaluate the flight data. We have tremendously extraordinary results. So we got all the data through telemetry, through the onboard recorders. We have tackled the main features of aerothermodynamics, high temperature material performances, guidance, navigation, and flight control. We are really very much satisfied about the flight results.
Aerothermodynamics, this is something Brian may talk about a little bit later on, and British interest in this as well.
Definitely, the next step will be with UK on board, and we are very happy.
We like that. Now, thank you very much, Giorgio. Now, before you spend billions on building a spacecraft like Bepi Colombo, which is going to be exploring Mercury in a few years, you're going to have to make sure that it isn't going to fall apart on the launch pad because of the vibrations. And in a few minutes, I'm going to show you how they test for that.
Thanks, Alice. Aerothermodynamics, what do you think?
Oh, I could talk for hours about it.
The floor is yours.
Oh, you're too kind.
Anyway, we'll be back with Della shortly. Before that, let's go back to Leicester, where Lucy Green was trying to get some special pictures of the sun during the eclipse. Let's find out how she got on.
Thanks, Brian. Well, yes, I am here in Leicester. The festivities are sort of dying down a little bit now. We've got people mulling around. But actually, we were up and hard at work even before the eclipse started. We launched a high-altitude weather balloon to try and catch a clip of it. And in fact, Dave is the person who launched that very weather balloon. So we've got the data back. We've got the balloon down. So, Dave, let's have a look. We can see that the balloon is bursting here. Bang, there it goes. It came flying back down to Earth. And then the first data are coming in. How do you feel about seeing this? How high is the balloon at this point?
That's about 30 kilometres, which is about 3 times the altitude of a jet airplane. And there's lots of cloud there, and Leicester is just below. So we launched it to a clear blue sky.
Yeah, I think it's remarkable that we got that break in the clouds. And here, look at that blackness of space. Incredible view.
Yeah, and there's the blue line of the atmosphere just there. And we launched just under here. So we were very lucky. Look, just surrounded by clouds.
We really were. Now, I want to see the images of the eclipse. So let's see what was returned. What do you think?
Yeah, we had the camera with it's great. It's better than we thought. It's a camera with a solar film on it. It's exactly the same as on the glasses that we used to look at the eclipse. And that's the view it got on the way up.
And it's a little bit blurry, but we should remember that this was just launched with a simple weather balloon. This wasn't expensive kit, was it?
No, it's very cheap and it's moving as well, so it's a bit blurred. It's fine. It's better than I expected.
Congratulations, and I understand that was your 50th launch as well, so well done on catching an eclipse with that. Now, we have had another significant project running here as well today, and that's been helped by none other than BBC Weather's Peter Gibbs, and he's here to tell us how that project went. Peter, what have you been up to?
The National Eclipse Weather Experiment, Lucy, this was organised by Reading University to really harness the power of citizen science. So we've had over 200 schools taking part throughout the country, some of them here at Leicester, really enthusiastic as well. The kids are getting involved in this, lots of amateur meteorologists as well, and we've had lots and lots of really useful information.
Well, I'm really pleased to hear that people have been getting on board with this, but tell me, what have you found in the information, in the data?
Temperature looks really good, particularly in the areas where we had clear skies. The temperature was about 2 or 3 degrees lower than it would have been without the eclipse. In the cloudier areas, a little bit less because that damps the effect, but about a degree showing up there.
And any sign of this mysterious eclipse wind that people speculated might happen?
The eclipse wind, a tricky one. Cloud was good though. We saw cloud cover dispersing. That's a first for a look at the whole UK, so that's a tick in the box for this experiment. The elusive eclipse wind is still elusive. The winds were quite light here. We saw some signs here in Leicester, but more research needed on that.
Excellent. Well, thank you very much. Now, things are slightly calming down here, but in any case, I need to head over to those telescopes where I'll be finding out a bit more about our familiar North Star.
Thank you very much, Lucy. Now, one of the things we hoped to see during the eclipse, but didn't, it wasn't all a success, was the stars behind the sun. Now, they've always been of significance historically because they are the constellations of the zodiac. But astronomically, what does that mean? To understand the zodiac, you need to see the stars behind the sun. They're normally too dim to see in daylight, although you might spot them during an eclipse. At the moment, Pisces takes pride of place. But as we orbit around the sun, a different constellation appears behind it each month. Ancient astronomers named this ring the zodiac, meaning circle of animals. And they use it as a celestial map to help chart the passage of the seasons. Dr. Radmila Topolovic is an astronomer at the Royal Observatory, Greenwich.
The zodiac band was very important for our ancestors. They used it to help with their agriculture. They needed to know when to plant their crops, when to reap the harvest. And the way they knew that was by looking for the signs of the zodiac, which they use as a giant calendar, essentially.
Ancient astronomers didn't stop there, though. It was the Greeks who came up with the idea of the personal star sign. Character traits determined by the constellation behind the sun on the day you were born. The astrologers ran with this. And that's where the problem started, for the astronomers out there. Because the dates of the star signs were fixed over 2,000 years ago when the zodiac was first devised. And since then, well, things have changed a bit.
The Earth is affected by the gravitational pull of the Moon and the Sun, and they introduce a wobbling effect in the Earth. That whole effect is called precession, and the Earth itself behaves a little bit like a spinning top.
This spinning top completes a wobble every couple of seconds. The Earth is a little more cumbersome. It takes about 26,000 years. The result is that since the signs were fixed, the constellations have drifted by a whole month.
Let's say you were born towards the end of January. This would mean that the sun should be in the constellation of Aquarius. But in actual fact, if you were to look at where the sun is on the day of your birthday, you would see that it's not in Aquarius at all. It's in the neighbouring constellation of Capricorn.
So now your star sign is not the constellation behind the sun on the day of your birth. And if that wasn't disappointing enough, there's another surprise in store. Enter Ophiuchus the Serpent Holder. His constellation was missing from the original zodiac.
There are 12 signs of the zodiac, but within the zodiac band, there are 13 constellations, patterns of stars. And the 13th one is called Ophiuchus, and it actually squeezes in just between Scorpius and Sagittarius. It's not one of the 12 signs of the zodiac.
But still, the sun sits in front of Ophiuchus for a full 19 days a year. So if you were born between November the 30th and December the 18th, then why not claim yourself a totally new star sign? Hey, if you want to know what constellation was behind the sun on the day you were born, you can go to the Stargazing website and find out. That'll be a fun thing to do, because astrology is for fun. It's just not for making important decisions about your health.
Oh, God.
I'll take the letters this year, you know? You're constantly getting the letters. I'll take the passion.
Address your anguished cries at the advance of reason to Dara O'Brien at bbc.co.uk.
Now, earlier tonight, we left Dallas Campbell at the European Space Agency Testing Centre in the Netherlands, preparing for a bone-shaking demonstration. Dallas, are you ready for liftoff?
Thank you, Brian. I think you'll enjoy this bit. I am now standing on one of 6 dedicated vibrating platforms. This is where they actually shake many tons of satellites and other spacecraft, which cost a lot of money. I'm going to get off the vibrating platform for reasons which are about to become apparent, and meet my new friend Matteo Apolloni, who's standing over here. Nice to meet you. You are in charge of this. How are you doing?
Very good.
Good. Can we turn it on and see if we can get it working? Yeah. Thank you very much. So. Let me just ask, so the whole point of this, if I'm right, is to do the kind of launch profile of a real launch, so you can actually see how the vibrations will affect spacecraft that are already built.
Yeah, the idea is to reproduce the same type of environment that the spacecraft will experience during its launch. So we want to get it safe up there.
I've got to say, you must have the most stressful job in all of ESA, because you've got people who've been working for many, many years with many, many billions of euros on these satellites, and then you get to shake them, and hopefully bits don't fall off.
Yeah, absolutely. I mean, I'm not alone, I'm part of a team, but definitely when the spacecraft is up on the shaker for the first time, it's a quite stressful moment for us.
You look very calm. Okay, so it's getting quite loud. So tell me what's going on here. Tell me what actually happens from start to finish.
Yes, I mean, this vibration table is sweeping frequency, as we say. So it's starting from 3 times per second, and it goes all the way up to 2,000 times per second. And the idea here is just to see what are the resonance frequency of the main structure.
The resonance frequency. Oh, so you start at one end of the frequency and then get smaller and smaller and smaller and smaller, covering the whole sort of gamut, if you like. How is this one doing? How are we doing now?
So far, so good. I mean, we just heard the first resonance frequency of the structure, and now we hear some more coming up.
Nothing has fallen off so far. I should point out, before we go on, that we haven't spent billions and billions of euro on this. They have built this specially for us. This is Stargazing Live's very own satellite, due for launch never, but so far it's intact and the antenna is still on. Now, what's going on now? Are we up in the sort of high frequency range?
Indeed, we have the second resonance frequency, which is getting quite loud, and everything looks safe, though.
And in your experience doing this, has anything gone wrong? Has there been sort of catastrophes?
I would not say catastrophe. Many things can go wrong. I've never seen anything breaking off, but I've seen more than once things not going according to plans, let's say.
But it is obviously a very important job, and I've been lucky enough to witness a launch, and I know how dramatic they are. Anyway, that's enough from ESTEC. ESA have been absolutely fabulous opening their doors to us. That is Brian's Christmas present sorted, the Stargazing Live satellite, and it's already gift-wrapped.
I'm looking forward to that, Dallas. I'm looking forward to receiving that through the post.
And I'm glad it's holding together, because space is the only place we hadn't sent Lisbon in over the last 5 years. Thanks, Dallas. There's another probe that will go through what Dallas has just shown us, the Solar Orbiter.
Now, the European Space Agency is planning to fly closer to the Sun than any mission has ever gone before, and Liz went to find out more.
I'm heading into the peaceful Surrey countryside. Perhaps not the obvious place for a state-of-the-art research centre. But since 1966, this grand Victorian house has been the home of the Mullard Space Science Laboratory, an international community of scientists and engineers at the cutting edge of space science. And it's thanks to this remoteness that they can be at their most creative here, collaborating, inventing, and building the most advanced space systems in the world. The lab is playing a crucial part in the new mission, called Solar Orbiter. Set to launch in 2017, it will fly even closer to the Sun than the nearest planet Mercury orbits, and face temperatures of over 500 degrees Celsius to learn more about what drives the Sun's dynamic behaviour. One of its main tasks is to sample the solar wind, just minutes after it leaves the Sun's surface. There's no scientific instrument in existence capable of that task, but engineers here have risen to the challenge and built their own from scratch. The high-tech task of creating the components for their solar wind analyzer is led by Simon Hemsley in what was once the garden's potting sheds.
This is the solar wind analyzer. There's over 150 parts in that.
In this?
In that. And they're all handmade here. And if you see over here, the front of the spacecraft is 500 degrees centigrade.
Yeah.
And has a special heat shield to protect the rest of the satellite from obviously disintegrating.
Indeed.
Their air instrument, right at the back in cold space, is at minus 140 degrees. Nice. And it never actually sees the sun.
Hopefully, if the orbiter does its job properly. I mean, one wrong move and you're singed.
Toast.
Yeah. This will be the only instrument in space that can capture the solar wind in this way and reveal what it's made of. It's set to take our understanding of the sun to a whole new level. What's really exciting about this solar orbiter mission is that it's providing a missing link in our current observations of the sun. Here in Stevenage, the main body of solar orbiter is being built. Dr. Nicolas Croissart is the man responsible for assembling the probe and keeping instruments like the solar wind analyzer safe from the sun's intense heat. The spacecraft's heat shield has to deflect the 500-degree heat from the sun to keep the rest of the satellite below a cool 70 Celsius. It will rely on a unique and surprisingly low-tech coating.
We use this amazing material, which is just crush burn animal bones. So that's basically how it will look like.
How did you come up with that?
Well, we did consider a lot of different materials and technology, and did a lot of different testing as well to prove that the concept was working, improve it, and just does the job.
How are you going to feel when it is launched? Can you even anticipate what that's going to feel like?
No, it's going to be a first for me. My heart will be pumping hard, I'm sure.
When it launches in 2017, Solar Orbiter will offer us the chance to find out how the solar wind behaves on its journey from the sun and how it can affect us here on Earth.
We've been joined by Liz again with other great shots, including one that you took yourself.
Yeah, well, not take myself,
yes,
but Mark Pingill took it. We had a wide-angle lens also in the plane, and during totality, everybody's focused on the eclipse, but actually there's other great things you can see, including the planets that are on the ecliptic, and that's Venus. There, look at that.
That's very good.
Isn't that very good? And you, in principle, you could also see Mars and Uranus here, and then Mercury and Neptune here. But there was a lot of light scattering up there at 28,000 feet, so we couldn't see them. But that's very good.
It is beautiful, that, isn't it?
Yeah.
And then we've got a stunning picture from the Met Office. They sent us one from their weather satellite. So this is the weather this morning. And there's the shadow. So there it goes.
Amazing,
across, and then that was the end of the eclipse. So can you see that one more time? Because I think that's really a very beautiful image. So you see all the clouds moving. So I suppose that's a couple of hours, isn't it? Because that'll be first contact.
Yep, and then 2 hours across the country.
Another great picture kinetic for the Proba 2 satellite. Which
this is great because it's
fantastic. and what do you find impressive is?
It orbits it twice, and it shows up features of the corona in extreme UV. These loops and flares, fan shapes from the corona. Really pretty.
Just one comment there. The reason that there were 2 eclipses in short succession is because of the orbit of the satellite itself, and not because Newton was wrong.
Yes. Other fabulous pictures, of course, coming from viewers as well.
Oh yes, we've got this is one of my favourite picture from a viewer actually. It's from Samantha Cristoforetti, who was viewing from the International Space Station, and this is an image of the shadow over the UK from the ISS. So thank you, Samantha, for that. And then this one here is an image from Paul Burton, and the reason I like this is because it's from my hometown, Oldham, and Paul Burton is also my electrician and friend, amongst other things. So I'm very pleased that he sent that in. But that's the eclipse from Oldham.
Delighted you could get involved. Now, well, talking about the great pictures we've had in, this brings us neatly on to the challenge set for us by Chris Linter. Chris, we had a challenge against many photos of Orion. Why were we doing this?
We were doing it to try and create a wide image that showed us some of the detail that you'd normally need a telescope to see. We got 790 images sent in, mostly from Scotland, where it was clear last night. Each of them looked a bit like this. It's a fairly typical image of Orion that you
normal cameras, camera phones.
Yeah, no telescopes involved. So one image looks like this, but you put them all together with a bit of mathematical magic, and we get something really stunning. And the magic of this image is if you zoom in, and more stars just start appearing. And then look at that by the left of the belt stars. That's the Horsehead Nebula there.
I just need to say, because that looks like almost like a Hubble Space Telescope picture, not quite, but it's on the way.
The place you see these details across a wide field. Go down, look at this. This is the Orion Nebula.
Wow.
And you see the famous bit in the middle, but look how far that extends. This is a new way, we think, of capturing the faint details in the sky.
I should emphasise that. So this has not been done before in this way.
No, we've used it on individual objects, but not for a whole constellation.
So what we're doing essentially is using a big telescope collects a lot of photons. 798 of the cameras collects a lot of photons, and when you merge them together, you get an incredibly detailed.
It's a beautiful image. We're going to put it on the web so that everyone can download it. And in particular, if it was your images that made this up, your pixels are in there somewhere.
And can people carry on doing that?
Yes, please keep uploading images. There's a link on the Stargazing Live website, and I think we'll use this as a way of monitoring the sky. So we'll do the whole thing.
Fantastic. OK, and we can still add more photographs to make a better image. If you want to take part, there's still time. Here's Lucy to show you how to find Orion.
Thanks, Dara. Yes, to find Orion this evening, turn and face towards the west. And in fact, we have a fantastic view of it right now because we have beautiful clear skies. And at the moment, Orion is dropping down towards the horizon, and it will be setting in just a few hours' time. The reason that Orion sets is because all stars during the night actually circle around the night sky. Well, all except for one very special star. I've invited these budding astronomers to accompany me on my expedition to the celestial North Pole. So head this way. We're in the Kent Downs and the view is spectacular.
It's staggering, isn't it?
It's just amazing. It's wonderful. It's just dazzling, the number of stars that we can see twinkling above us. But there's normally one star that everybody has heard of, and that's Polaris, or the North Star. Is that a name that's familiar to you?
Yeah.
It's a signpost to help us hop on to other constellations. But tonight, I want to show you that there's much more to Polaris than just that.
With the naked eye, the North Star is seen as a constant, solitary point of light. But looking through a telescope gives a different perspective.
Tell me what you can see.
I see a bright star on the left and a fainter star to the right and just above it.
That view that we're having is showing us that Polaris isn't an object by itself. It actually has orbiting companions.
It's pretty amazing.
The star we see with the naked eye is a supergiant, with around 6 times the mass of our Sun. The tiny companion you can just see next to it is a quarter of the size and rotates around it from 240 billion miles away. And this isn't the whole picture.
Polaris is in a triple star system. There is a third star that's far too faint to be picked up in a telescope this size. You need something like the Hubble Space Telescope to see it.
This third companion was first seen in 2006. The image shows how closely it hugs the primary star. Even Hubble could only just pick it out. But there's something even more surprising about our North Star.
Polaris is famed for holding its position over the night, and all the other stars move around it as the Earth spins. But over time, Polaris is actually going to start to drift away from the North Pole, and it's going to lose the significance that it currently has.
Over the centuries, our North Star has had multiple identities. The gravitational pull of the Moon and the Sun causes the Earth's axis to wobble and shift 1 degree every 72 years. And that passes the responsibility of our celestial North Pole from one star to another. 5,000 years ago, when the Egyptians were building the pyramids, they looked at a different North Star called Thuban. It's part of the constellation of Draco the Dragon.
They would have had an even better view than we have tonight because they would have had no light pollution at all. So it's really a lovely way to connect us back to those early civilizations.
Looking to the future, the next star to take up pole position is a star called Gamma Cephei. It's part of the constellation of Cepheus the King. It looks like a child's drawing of a house, with Gamma Cephei marking the peak of the roof.
And that star will be above the North Pole in around 2,000 years' time.
When our descendants look up at the night sky, it is Gamma Cephei that will appear fixed in position, and Polaris will join the rest of the stars dancing around it. Over time, 6 prominent stars will share the honour of appearing closest to the celestial North Pole, and our current one will eventually return to reign in 28,000 AD.
So actually, there's a whole family up there. Current North Pole star, it's just one in a generation. And there we have a live view of Polaris right now. And in fact, you can also see one of the companion stars. But there's something else that makes Polaris interesting. It's a star that changes in its brightness. We'd call it a Cepheid variable. And after a few decades of dimming, the brightness is currently on the rise again. Now, if the ancient data from the Greeks is anything to be able to be relied on, we think that Polaris is around 2 times brighter today than it was back then. So really something to enjoy. Now, we've had a fantastic time here this evening under these clear skies. But for now, it's bye from Leicester.
Thank you very much, Lucy. For the last 2 days, we've been asking you to help us find exploding stars, supernovae, in order to help us refine the known age of the universe.
Now, the reason we're asking you to help is because they're extremely rare. 1 per galaxy per century. So if you looked at an average galaxy, you'd have to wait, on average, 100 years to see a supernova explosion. And the critical thing for astronomers is to see them as soon as possible, because we want to see how their brightness changes over time. You only see them for about a week. Now, there's one astronomer, only one in the world at the moment, we think, who's been lucky enough to catch one in the act of exploding. That's Alicia Soderberg from Harvard University. Lisa.
Hi.
It's good to have you here. Where were you looking when you captured this rare event?
Right. So I was actually using a satellite, NASA's SWIFT satellite, when I captured this rare event in the X-ray regime.
And you were looking at something else, presumably?
I was specifically looking at another supernova, which is an anomaly, in the sense that this galaxy, which looks just like the Milky Way, produced 2 supernovae within short order, within just 2 weeks of each other. So this is the supernova I was looking at, supernova 2007 UY. It was the last supernova observed in 2007, discovered on Christmas.
Yeah, so that's the 6th of January, this photograph.
This is when it was, this is when we've got our first data from, and an amateur reported it. And then a few days later, we observed it again. And this time, we saw a new object that appeared in the same galaxy.
How did it appear? What was the sign that it was appearing?
So we saw an X-ray signal, a booming X-ray signal that actually saturated and the entire image as seen by the SWIFT X-ray satellite.
So this is the X-ray signal here of the supernova exploding, and this is it, what, about, 2 days before?
Yes. So this is, we can actually mark the explosion date to within about 9 seconds.
And how long was the signal?
The signal lasted about 3 to 5 minutes.
3 to 5 minutes?
I really would Talk about that a little bit. So this star, what do we know about the star? How big's that star? How massive?
So we actually know that it started out probably about 20 times the mass of our sun, and it lost a lot of material. So the time it died, it was the radius of our sun, with a mass of a few times the mass of our sun.
Right.
It lost all that material through its own winds. It's a very windy supernova.
And then it collapsed.
Yes.
And you get a pulse in that. Because you've still got a star that's around the size of our sun, as you say.
Yep.
But something happens to it fast enough to send a pulse of X-rays out in 5 minutes.
Yep. You're just left with the core of the star, and the rest just goes out.
And then you sent the word out that you'd seen this pulse of X-rays. How long before optical light followed that?
So I sent the word out, and people responded from all over the globe, and it was about 24 hours.
Wow, a day later we're beginning to see it.
And that's how we identified this new transient object that supernovae are not discovered in the X-rays. So that's how we identified it as a supernova, because we had an optical signal that we could classically identify through this standard system.
And because the original one that you were looking at, that wasn't discovered by a professional astronomer either, was it?
No, that was also an amateur.
It was an amateur. I mean, this is part of the thing that we're enjoying doing here. We're getting amateur astronomers to help us.
Exactly.
One thing that Chris is doing. Chris, the whole project we had was to get amateur astronomers to look at data to find things, and we've had success.
We have. Our data didn't come from amateur telescopes, but from a telescope in Australia. And our volunteers, viewers from Stargazing Live, have reviewed 1.5 million sets of images like this. The one in the middle is a library image, a reference image from a few weeks ago. On the left, though, there's something that's appeared. That's an image from just yesterday, and so that's a new supernova.
So that's the new star in the centre.
We showed you one new one. Last night we got 3 in the last 24 hours. There's another one here in a galaxy, and if you flick on, you'll see there's an image from a telescope in Chile, which we were using to follow up. So the yellow thing's the galaxy, and the blue dot there is the supernova.
Now, this is a different kind of supernova, isn't it? It's the one that Alicia was talking about.
That's right. These are Type 1a, or 2 of the 3 that we found last night are Type 1a supernovae, and they're the ones that we can use to try and measure the expansion of the universe.
And you've got to tell us how, because we've got to remember the age of the universe.
Right, so you need 2 things. So one is that the reason we care about Type 1a supernovae is that they always go bang with the same power, the same luminosity. And so if you know how bright they were when they went bang, and you know how bright they appear in this image, that gives you a distance. So we have a measure of the distance to this galaxy. And then the other thing we need is the redshift.
Yeah, there's another thing you can measure. So light is a wave. So you imagine a wavelength like that. So the distance between the 2 peaks is called the wavelength. What we find is if we look at the light from these supernova, the light is stretched. And the interpretation is that the universe, space itself, is stretching. So let's say that light stretches by 1%. We call that a redshift of 0.01. What's the redshift?
It's about 0.04, so about half of that. So the
4%.
point is that you've now got a distance from the brightness, and you've got to measure the expansion. You put those 2 things together, and you can work backwards to get the age of the universe.
So it's an easy calculation. Let's say the supernova was 1,000 light years away, and the redshift was 0.01, so it's stretched by 1%. That means that in 1,000 years, which is the time it took light to come from a supernova to our telescope, the universe is stretched by 1%. And so you can see how you calculate the age of the universe.
Right.
Roughly speaking, if it's stretching at that rate, run time backwards, you can work out.
And have you made this calculation?
We have. So let's imagine we're in a simple universe, and the only thing we have is this supernova. I've got, well, it's a front of the envelope calculation, but the answer's here.
I love this.
The universe would be 14.03 billion years old just from this supernova.
Now, that is, from what we know is the known age of the universe, how far is that off?
It's a couple of 100 million years out. But what we'll do is we'll keep watching the supernova, we'll refine our measurements, and what we'll really do is put it in with thousands more. And we need people to keep finding these things. So we've still got data up from the last 24 hours at snapshotsupernova.org.
I just think we should emphasise what a wonderful measurement that is, because you can do it from one single measurement. Like the professionals, of course, people like you do it with. How many supernova have we got now in that?
Oh, about 10,000 at this
Many
point.
thousands.
Yeah.
But I think for me, the fact that you can take one measurement, and there's only 2 things you can do. You look at the brightness, and then you look at the redshift, just the stretch of the light, a direct measurement. And from that single measurement, you can estimate the age of the universe. And you don't get.
I don't get a silly answer.
100 years. You don't get 6,000 years. You get.
We will now add this to the pile of data we have.
We will, and
Do
we'll
we
keep
think this
looking
will say
as
that
well.
the universe is older than it was?
Yeah, so this is slightly
Our
older.
guess
So you would guess that if you put this in the pile, it would make the universe very slightly older.
Okay, now we're going to have more discussion about that on Back to Earth with minute. Your boat today. We'll also talk to, I believe, 1 or 2 of the amateur astronomers who found this. That's all going to occur in a second.
Can I just say that that's why I love physics?
Oh, just say, you always tell me why you love physics. And what a few days we've had here, by the way, between this and meeting Buzz Aldrin.
Meeting Buzz
and the
Aldrin,
eclipse,
terrific eclipse.
discovering supernova. It's been a fantastic couple of days. Thank you for joining us over the last 3 evenings and that magical morning this morning when we saw the eclipse. We're going to be back here in 2 minutes' time for more discussion, a few drinks, a relax. We'll get through all of these issues. But for now, I think we're going to leave you with some of the most beautiful images from today's eclipse. From everyone at Stargazing, thank you very much. We'll see you in a minute.